In this video, we shall look at energy in simple harmonic motion and do a few review problems associated with it. First, a brief introduction. Let's assume you have a block with mass m and it is attached to a spring with spring constant, let's say k, and you pull this block slightly to the left and then release it, and this will lead to simple harmonic motion of that block, and it will go back and forth as indicated by the arrow. Now let's assume that this is the so-called equilibrium position, and that is the maximum displacement position on the left, and this is the maximum displacement position on the right of that equilibrium position, and that distance is known as the amplitude on both sides. I am using the negative sign here to denote that if this is the x-axis, so the rightward is the positive x-axis and the leftward direction refers to the negative x-axis, hence the negative sign in front of that A. Since this block moves at any one point, say at that point where the displacement is x and the block is moving with some speed v, the block would have both the kinetic energy and elastic potential energy. The kinetic energy is given by half times the mass of the block times the square of the speed of the block at that point. So let's say the speed there is v, so that is the v that shows up in this equation. Likewise, its elastic potential energy is given by half times spring constant k times the square of the displacement, namely the distance between the equilibrium location and the present location of the block, because in this case that distance gives the amount of stretch for the spring. Conservation of energy says the sum k plus u has got to remain constant. Let's call that constant capital E, and E refers to the total mechanical energy of the system. When the object or the block moves at the equilibrium position where the stretch is 0, there is no potential energy, but there is kinetic energy, and the kinetic energy at that point is maximum. So we write the maximum kinetic energy equals the total mechanical energy. Likewise, when the block gets to the extreme positions, namely when it is at the amplitude location, it stops. That means there is no kinetic energy and there is only elastic potential energy. And in that case, we write U max, so the elastic potential energy is maximum there, equals the total mechanical energy. Now let's look at the problems. Problem 1. A 0.5 kg object is connected to a spring with spring constant 20 newtons per meter, and the object oscillates on frictionless surface. So let's assume this figure here is demonstrating what is happening to that object. Now the amplitude of the motion is measured from that equilibrium position in the middle, and let's call that amplitude A. A there and A on the other side. So the block moves back and forth like that, about that equilibrium position. Find the total energy of the system and maximum speed of the object if the amplitude of the motion is 4 cm. So that means this point and that point is 4 cm measured from the middle. So this is the 0 cm mark, and that is minus 4 cm. So let's do part A, the total energy of the system. Now we are given the amplitude, which means we can calculate the amount of energy the block has here or there, because at those points the energy is purely in the form of elastic potential energy. There is no kinetic energy there because the object is not moving there, so there is no speed, no kinetic energy. As we have discussed a few minutes ago, the elastic potential energy at those points is maximum, and the expression is given by half times the spring constant k times the displacement squared. The displacement in this case, it is just the amplitude, and square that. So K is given to be 20, so that is 20. We know the amplitude. The amplitude is 4 cm, so 0.04 meter. Don't forget to square it. And your answer is 0.016 joules. And this is the total energy of the system. It does not change, doesn't matter where the object is. Next, the maximum speed of the object. The maximum speed of the object occurs right there at the equilibrium position in this case. So the maximum speed would give maximum kinetic energy, and that is given by half m the square of maximum speed. Now we know that at the point of equilibrium where the kinetic energy is maximum, the elastic potential energy is 0 joules. So E is K max plus 0 at that point. Now we know what E is. E is 0.016, that is the total mechanical energy of the system. And K max is just that, half mass square of the maximum speed. Since we know what the mass is 0.5 kg, we can determine V max. So V max equals 2 times 0.016 over 0.5 square root in the unit of meter per second. And when you do the sum, you get the following: 0.253 meter per second. So I have recorded the answers to part A here. Now let's do part B. What is the velocity of the object when the displacement is 3 cm? So let's assume the object or the block is here and the displacement is 3 cm. How fast is the object moving there? Again, we can use the energy principles to get that answer. At that point, when the displacement is 3 cm, the elastic potential energy is given by half. K is 20. The displacement is 3 cm, so turn that into meter, 0.03 meters squared. Plus the kinetic energy there is half times the mass is 0.5. Velocity we don't know, so the square of the speed, let's just write it v squared. The total must be the same as the total mechanical energy of the system. That does not change. This is just conservation of energy. So we equate the sum to 0.016 joules. And you see you can solve for the v, namely the velocity of the object at that displacement. And you get 0.167 meter per second. Of course, in this particular example, if we are talking about the direction of motion that way, then this answer would be negative 0.167. If the object is coming back in a rightward direction, then we express the answer for the velocity as positive 0.167 meter per second, because we have taken that direction to be the positive x-axis direction and that to be the negative x-axis direction. Again, we have written the answer to part B there. Now part C, find the kinetic and potential energies of the system when the displacement is 3 cm. The potential energy of the system at that displacement is quite simply given by half times the spring constant 20 times the square of the displacement, so 0.03 squared in the units of joules, and that's going to be 9 times 10 to the power minus 3 joules. The kinetic energy can be determined from the conservation of energy principle. So E, the total energy, equals the sum of kinetic energy and the elastic potential energy. Now we know the total mechanical energy is given by part A, 0.016 joules. Kinetic energy is what we want to determine. Potential energy has been determined above, 9 times 10 to the power minus 3, and you can calculate the kinetic energy for that displacement, which is 7 times 10 to the power minus 3 joules. And that solves this problem. Problem 2. A simple harmonic oscillator consists of 0.5 kg block attached to a spring. The block moves back and forth along a straight line on a frictionless surface with equilibrium x equals to 0 meter. At t equals to 0 seconds, the block is moving at x equals to 0 and moving in the positive x direction. A graph illustrating the magnitude of the net force on the block versus a position is shown below. So F versus position. Find the amplitude, the period of the motion, the magnitude of the maximum acceleration and maximum kinetic energy of the block. Let's do part A. The amplitude. The graph shows the maximum position measured from x equals to 0 point for this block is 0.3 meter. So that means that amplitude is just that, 0.3 meter. This graph illustrates the so-called Hooke's law, where k is the spring constant. So when x, the displacement or the amount of stretch of the spring, is maximum, namely the amplitude, the force is also maximum, in this case with a magnitude of 80 newtons. Part B, the period of motion. Period is written in the following manner: 2 pi over the angular frequency. The angular frequency for such a harmonic oscillator is given by the square root of spring constant over the mass of the block. So period is defined as 2 pi square root mass of the block over the spring constant. We know the mass of the block, 0.5 kg. How do we determine the spring constant of that spring? Well, we just use Hooke's law that we talked about a few minutes ago. F equals to kx. I'm talking about the magnitude of F, so there is no need to put the negative sign there. From the graph, when F is 80 newtons, x is 0.3 meter. So that means k is 267 newton per meter. Now we can determine the period. The period is 2 pi square root 0.5 kg, k is 267, in the unit of seconds, which will give you 0.272 seconds. Part C, maximum acceleration. Acceleration is position dependent, and we know it's given by minus the square of angular frequency times the displacement. So the maximum acceleration is given by minus the square of angular frequency times the maximum displacement, in this case the amplitude. So the magnitude of the maximum acceleration is omega squared times a. Now we know what omega is. Omega is a square root of k over m. So omega squared is k over m. Amplitude is 0.3 meter. So what is k? The spring constant was determined earlier to be 267. Mass of the block is 0.5 kg times 0.3. And will give you 160 meter per second squared for the maximum acceleration. Now part D, maximum kinetic energy of the block. From energy principles, we know the maximum kinetic energy of the block is given by the total mechanical energy, which is itself can be the same as maximum elastic potential energy, and that we can calculate. Half times the spring constant times the square of the amplitude. So you get half times k is 267, that's from here. Amplitude is 0.3, so 0.3 squared, which will give you 12 joules as an answer for part D. And that solves the problem. As always, thank you for watching.